Welcome to the weekend work focused on Chapter 6. This is going to cover the first part of Activity 6A. Before we start the activity, I just want to point out that the purpose of Chapter 6 is to deepen our knowledge about exactly how do atoms share electrons in covalent bonds. So if we take the simplest covalent molecule, here we've got a hydrogen atom. I've drawn its Lewis representation. In other words, I've drawn its symbol and a valence electron for hydrogen. And here's another hydrogen. I've drawn its valence electron. And of course, this is how we draw its Lewis structure for the molecule. Now, if we go back to earlier parts of the semester, one way we can represent this is with a shell model where we've got a single proton and then the valence electron, a single proton and the valence electron. And of course, the other way we've represented hydrogen is with its electron configuration. So the question is, when we put atoms together into this molecule, what does that really look like? What happened to the atomic orbitals? Where are the electrons now if they're not in atomic orbitals? What does that look like? And we might envision a kind of simple picture in which the valence shells of the two atoms just overlap. And it might look something like this, where you've got the two different protons, and now you've got this space where the electrons are in a kind of shared space in the middle. And for hydrogen, well, that might be pretty satisfying. After all, the valence shell of hydrogen is a 1s orbital. It's spherical. Maybe that's all that needs to happen. But what happens if we take a slightly more complex atom and put it in a molecule? For example, if we wanted to take a hydrogen atom and a fluorine atom, so here's hydrogen with its 1 valence electron, fluorine with its 7 valence electrons, we put them together, that's how we represent them in a Lewis structure. But really, where are these electrons and what kind of orbitals are they in? If we look at other models that we have for these atoms, what we're reminded about is that hydrogen has a single valence electron in its valence shell, and its electron configuration is 1s1. If I represent just the valence configuration of fluorine, it's got a core charge of +7, so this is not its nuclear charge. Its nuclear charge is +9, but I'm only showing the valence electrons on the core. And these are the valence electrons, 2s2, 2p5. The 1s2 electrons are not shown because they're not involved in bonding. So the question is, we've got electrons in here in the s orbital, which is spherical, and the p orbitals, which remember are these funny dumbbell shapes. So what's going on? How do those come together to form a bond? And we can draw a picture, and it might look something like this, where now those two electrons are shared in between the nucleus of hydrogen and the nucleus of fluorine. But really, this doesn't tell us what's going on with these original atomic orbitals. So Activity 6A is going to begin to build our understanding for this. So in this recording, we're going to just focus on Model 1. And what we're going to learn here is that the electrons in a molecule are going to be involved in hybrid orbitals rather than atomic orbitals. So we've already learned how to determine the shape of electron domains and around a central atom. And we do that by looking at the Lewis structures. But we have to go a little deeper to understand exactly what's happening with all those orbitals. So valence bond theory is one theory that attempts to describe what is it that's happening. And it describes that the electron pairs around a central atom are in a set of orbitals, and remember, an orbital is just a domain or a region of space that is hybridized or constructed from the usual set of atomic orbitals for the atom. So we're going to make them out of SPD orbitals from the atom, and we're going to label them as new orbitals that reflect which atomic orbitals were used to construct them. So in this first part, we're just going to learn the labels. It's not really going to make sense in terms of what's going on, but we're just going to learn some terminology that we can use to label what's going on. So here is the table that we're going to use. If we have a bond angle around the central atom that is 180 degrees, then the central atom is going to use what are going to be called sp orbitals. There are going to be 2 of them. They are made out of taking an s and 1 of the p's. That leaves 2 p's that are not hybridized, and the angle between the orbitals is going to be 180 degrees, and they're going to be in a linear arrangement. If the bond angle is 120, the hybrid set is going to be sp2s. There's going to be 3 of them. They're made out of 1 atomic s and 2 atomic p's. And the number of p orbitals that aren't hybridized then, because we used 2 of them, there's 1 left. That means there's 1 left over. The angle between the hybrid orbitals is 120, and they're going to be in a trigonal planar arrangement. Finally, if the bond angle around the central atom is 109.5, we're going to use sp3 hybrid orbitals. There's going to be 4 of them. They're made by combining the s and all 3 of the p orbitals. That means there's none that are not hybridized. And they are in a tetrahedral arrangement. One thing I really recommend that you do is you go to this website and watch. There's a little video of how the atomic orbitals get morphed into these hybrid orbitals. Now, you're probably like, what the heck? I have no idea what's going on. So just bear with me, we'll get there. The hybridization that is assigned to a central atom is based on the type of bonds that the atom has to form, and we can use the experimental bond angles, which is something we have already learned how to do, to determine what kind of hybrid orbitals we need. So for example, if the bond angle around a central atom is around 109, then we're going to say that the central atom is going to need a set of sp3 hybrid orbitals for bonding. Or we might say it's sp3 hybridized. Likewise, if the bond angle is 120, we're going to say it's going to be sp2 hybridized. So let's just practice applying those ideas. Here is a Lewis structure, and what I've drawn it in such a way that we now see that its geometry is tetrahedral. The bond angle is 109.45, and that means that the carbon is going to be sp3 hybridized. If we look at this structure here, this bond angle, the HCH bond angle, is approximately 120. We know it's actually a little bit less than that because of the double bond. But because it's near 120, we can say that the carbon is sp2 hybridized. So we're just using the table on the previous page to apply a label. You shouldn't necessarily be able to picture what's going on yet. We're just learning the terminology. In this next example, we've got around the carbon to which the arrow is pointing, the hydrogen-carbon-carbon bond. Oh, look at that typo. It should be hydrogen-carbon-carbon bond is 180 degrees. And looking at the table on the previous page, that means that carbon is going to be sp hybridized. If we look at water, the bond angle around water is 109.5. That means that oxygen is going to be sp3 hybridized. And finally, if we look at carbonate, CO3 2-, this is its Lewis structure. Notice that it is one of these examples where we have to draw 3 different structures in order to represent the bonding in the molecule, because we can represent the bond angle, the double bond, as being here, here, or here. So we draw 3 resonance structures, and the true structure is an average of all 3. So look at here, another typo. This is the OCO bond angle. Let me do this one up here, HCC. The OCO bond angle is about 120 in this molecule. And so that's going to make the carbon sp2 hybridized. So that's it for Module 1. All we've learned is how to apply the labels. In the next video, we'll talk about really what do these orbitals look like and how do we use them.